Okay, now that we've talked about velocity and acceleration, I want to talk to you about another concept which is important and will lead to a lot of other different results. It's what I call density at a length. Not only do we have different sizes of gravity strings, but we have different densities at these lengths. What you'll find is that we'll have lots of very short gravity strings and very, very few long gravity strings. One of the effects that you already know about this is, for example, with the Earth. When you're close to the Earth, anywhere, let's say, 1,000 feet above the Earth, everything is pulled down very strongly. Why is that? Because there are so many gravity strings at that distance that every object is just pulled in by them. But then extend out for several million miles. There's only going to be a couple of gravity strings at several million miles. So an object comes by, yeah, it may touch a gravity string, or it may not. It'll just float on by. If it touches a gravity string at that distance, it might come in a little bit, bend a little bit, but it won't probably in. So there's a lot of different practical differences, effects. The way I like to imagine this is a good analogy. Is what I call grass, bushes, and trees. So take a nice little field. You have all this grass all over the place. You got a few bushes, and then you got a bunch of trees. How many grass blades are there? Millions. Millions upon millions. And they're only a couple inches tall. In that same region, you've got a couple bushes, let's say a dozen or so. Those are about, let's say, 3 feet tall. And then you got a handful of trees, let's say 5. And those are probably about 20 feet tall. So density, a lot more grass blades, handful of bushes, very few trees. Same thing happens with the gravity strings. Millions and millions of gravity strings that are very close to the Earth. Anywhere between a couple feet to a few thousand feet. And then they extend a couple miles, kind of like the bushes. There's a dozen up there. And then the atmosphere, like the trees. There's about 20 of them up there. And then, of course, there are people that are really tall that extend out towards the sun and the moon and everything else. So that is density at different lengths. And the importance of this, another importance of this when it comes to acceleration. When your particle comes in here, we don't just have, so we might have like 1 or 2 long strings and then do everything. When we encounter the medium strings, we're not just going to encounter 1 medium string, we're probably going to encounter 100. So not only is going to increase at a faster rate, we got 100 going in faster. And then we got something down at the, like I said, a few feet, we got millions. So not only again is it increasing because you have a few more strings doing their force carriage pull, you've got millions and millions of them. So by the time it comes down to 1,000 feet above the Earth, they're just smashing right into each other. That's a very important concept behind the density of a length. And it's also why once we have like a satellite above the Earth, it can stay up there. Because guess what? It's only going to encounter a few of these. Not much big deal. But when you're down by 1,000 feet above the Earth, man, you got millions of these gravity strings. Just over 1 square foot. 1 square foot of Earth, millions. And any particles, any boulders, a box, just going to smash one into each other. That's density of length. Now another concept I want to reach upon is the terminal velocity. So we talked about the fact that any object, such as the Earth, has several hundred different lengths of gravity strings. Well, obviously there's some point where it's the shortest. And on the Earth, the shortest gravity strings extend a few hundred feet up to, let's say, 1,000 feet in the air. Right? So let's say 1,000 feet in the air are the shortest gravity strings. Once all all those shortest gravity strings have been intertwined, there's no more. There is no shorter. So you can't increase the speed anymore because there are no more horses. There's no more horses to pull. So there's no more, you can't increase the speed. At that point, whatever the object is, that's as fast as it's going to fall. It won't fall any faster. So it's coming from space, it'll slowly accelerate. But once it reaches its maximum, there are no more gravity strings. It's not going to get faster. And physicists call this the terminal velocity. They've noticed that every object, once it reaches a certain distance above the Earth, will never fall at a faster rate. And that is because of the terminal velocity. Now, I can explain this because there are no more gravity strings. There are no more shorter gravity strings. Therefore, you can't increase it. It is what it is. And at that point, 1,000 feet, 500 feet, 200 feet, it's all the same. Same terminal velocity from standard gravity.